Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Numerical Integration, Approximating Definite Integrals using the Trapezoidal Rule and Simpson's Rule. As always, please be attentive as you watch this video. By way of introduction, there are two situations which it's impossible to find the exact value of a definite integral. Our go-to thing is to use the fundamental theorem of calculus, and so to evaluate as an example the definite integral from 0 to 1 of e to the x squared dx, what you would have to do is you would have to find a function capital F such that the derivative of capital F was e to the x squared. Well, there is no function like that, so that's not going to work. You might say, oh no, Jim, I can do this by substitution, and you would say, I'm going to let u equal x squared, but you see that's not going to work because when you try to do du, there's no x factor here. So you see there are some problems that do not allow themselves to be addressed by the fundamental theorem of calculus. The second situation arises when the function is determined from scientific experimental data or measurements, instrument readings, or collected data. Then you really don't have a full formula. There is no formula for the function itself. But what we're going to do is we're going to recall what we did. We can use the data points in terms of Riemann sums, where we look at left endpoints and take the limit. So you see this integral could be the sum, and n could be very large, that you slice it into rectangles, and that approximates the value of the integral. We could also take the right endpoints. We get a different number, but in the limit, again, it's going to be the same. We could do that, and we could also take any point in the interval, and that means that we could have taken the midpoint of each interval. So again, here you have rectangles, but you're taking the midpoint value. Now, if you look at these three pictures of the same thing, you say, oh, it looks like the midpoint might actually do a better job of approximating the area than the others, and that's actually true. Here is the midpoint rule. Now, this works. You can write a program to do this, but there are other ways that we're going to talk about. But this is what the midpoint rule says. So the definite integral from a to b of f of x dx is approximately equal to the midpoint that's found by making these rectangles, and we're evaluating this function. The height of these rectangles is going to be the function evaluated at the midpoint of each subinterval. And here you see, what the midpoints are and things like that. So that can work. And in fact, let's do that to estimate n equal 10 with n equal 10. That means 10 rectangles. The integral that we realized that we couldn't do using the fundamental theorem of calculus. So there's our there's our curve. There's our 10 rectangles, and notice we're taking the midpoints of each subinterval. And by the way, if I'm going to 0, 1, the first subinterval is going to go from 0 to 0.1, and so the midpoint of that is going to be 0.05, and so on. So these are the midpoints, and delta x is going to be the 10 rectangles. Each one is going to have a base of 0.1. So now we will evaluate delta x times this sum of values. And here I actually do the calculation. And now the exact answer is this, but I'm going to, in these cases, since you can't come up with an exact answer anyway, and this is not the exact answer because this is the value of the approximation. So we're approximating anyway, so we're plugging that into a calculator. Actually quite a bit of work, but you see you care to get an answer, so this is 1.46, and so on, rounded off. Now, another approach would be to use a different geometric figure, and this time we're going to use a trapezoid. And you might recall from your geometry, a trapezoid is a quadrilateral. It's a four-sided plane figure with only one pair of parallel sides. Now our trapezoids are going to not look like trapezoids you've seen for a while, because these are the pair of parallel sides. This other side is not parallel with that one, but these are now trapezoids. And so what we're going to do is we're going to again divide into equal subintervals the integral from a to b f of x dx, and so we take delta x to b equal subintervals to build trapezoids, and so these are going to be b minus a over n, and such that a is equal to, and we start with x0, we go all the way up to xn, we can take n to be as many as we want, and this is equal to b. So each of these forms a trapezoid, and in fact here is the first trapezoid that's formed. So you see the base is b minus a over n, and the heights of the that actually is the height of the trapezoid. This is one of the sides, and that's parallel to this other side, because both of these sides are parallel to the y-axis. So we're taking the area of the region that's approximated by using, in this case, that this picture shows, 4 trapezoids. And we do need to have the area of the trapezoid. And our formula for an area of the trapezoid, if we draw it this way, it's going to be 1/2 the sum of the 2 parallel bases, or you could think about that as being the average of the parallel bases times 8, where h is the height, or the distance between the bases. Now, if you look at our picture here, what you see is the difference between the bases is going to be b minus a over n, and the average of the bases is going to be f0, or actually I guess that could be f0 plus f at x1 all over 2. So that's the average of the bases. So this is the area of the ith trapezoid. Notice I have I minus 1 and I here. And so the sum, I just add them up. So the area is going to be, now each of those has a factor of the base, and here's the average of those. But the average of the bases. But I can pull the 2 out, as I did here, and then I have this. But notice that some of these sides get represented in 2 trapezoids. For example, we're looking at the picture down here. This first vertical line is only involved in the first one, but this next one, this one, is involved in this side and this side. So you see you have f of x1 plus f of x1. F of x2 is also repeated, and the only one that's not repeated again is the last one. So we're going to have b minus a over 2n, but each of these is going to be a 2 except for the last one. If we take the limit as n goes to infinity, we see definitely this does converge to the definite integral. So if I pick n big enough, I'm close enough to the answer that I want. And so the result is summarized in the following theorem, called the trapezoidal rule. So if f is continuous on AB, the trapezoidal rule for approximating the integral from a to b f of x dx is given by the definite integral is approximately b minus a all over 2n, and then I have this sum where I have a 1 as the coefficient here, a 1 as the coefficient here, but I have 2 everywhere else. And as n goes to infinity, the right-hand side approaches the integral from a to b of f of x dx. Actually, this is a very easy calculation. You see the coefficients follow this pattern. And later in this course, we'll reference this as an excellent applied example of a numerical sequence. We will study sequences and series in this course. So starting this in our eventual sequence jargon, we will say that t sub n, which is this, it depends only on n, and I know it depends on f as well, but it's a function of n. So t sub n converges to the value of the definite integral, this value, and we will write t sub n converges to the integral from a to b f of x dx. And I changed to capitals, but don't worry about that right now. Let's do an example, and we're going to do a function that you already know. This is sine x, so we're integrating from 0 to pi sine x. Of course, we know how to do this more readily. I'm just trying to show you how the trapezoidal rule works. So here is what I'm doing if I have 4 subintervals, and here's what I do if I have 8 subintervals, because I'm supposed to look at the results for 4 and 8. So if I let n equal 4 and do the calculation, and you should make sure that you do understand this calculation, I get this using the formula. and in the calculation I get this, which is approximately equal to 1.9. It's 1.896. Now if n is equal to 8, I get 1.974. And if you actually did this calculation using the fundamental theorem of calculus, you'd know that it is 2. So you see, we see here that the larger we take n, the closer we get to the actual value. And that will happen in general with the trapezoidal rule. Again, just summarizing, this is what we have for the midpoint rule, and this is what we have for the trapezoidal rule. And the trapezoidal rule can easily be applied to estimate integrals like we did in that example. And in fact, we could use it almost as easily, in fact, exactly as easily, if we're doing this one, the definite integral from 0 to pi of sine of x squared dx. Now, this is not sine squared of x, because what's getting squared here is the x, and you could put parentheses around the x squared, but math people really don't do that. And you might think, oh, I could do that by use substitution, but try it. You can't. It won't work. So you have to use the trapezoidal rule. So the trapezoidal rule can be applied easily to estimate this integral to any degree of accuracy. Okay, so now I'm going to finally ask you to do something. Use the trapezoidal rule and the midpoint rule. Use n to be 5 to approximate this integral. This is the definite integral from 1 to 2 of 1 over x dx. I know that you can do this without doing the trapezoidal rule and midpoint rule, but I'm asking you to practice those two here. So you know what to do. Let's see how you do. Actually, we'll see how you do when we pick this lecture up again. So in closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. God bless you all till I see you next time.